Today's lesson is the last of the concepts that we need to cover for this particular topic, and in my opinion is even easier than any of the others because it requires no numbers, no calculation, but purely just art. That's what this is, it's purely art and drawing. So this is all about transformations. And so what you've seen here is a totally legitimate polynomial. I actually just, basically what I did in my graph program, I put a long string of brackets all next to each other. I occasionally put a square on one of them, and I got something that looks like it needs to be returned back to whatever pit from hell it belonged to. But yeah, this is a polynomial that looks like it's melted in the sun. And essentially, one of the questions that we ask is, if we've got a graph that we have no equation for, and we need to work out what it looks like when it's done some transformations, what do we do? Now, when I see p of x plus 2, put your hand up if you can tell me what you reckon has happened to the graph. Mr. Daniels.
It has moved up 2 units.
Yes, it's moved up. So we're going to try to draw this blob, but moved up by 2. So I would start, it starts right at the intersection, so I'm going to move it up by 2 here. That's what I'm going to describe as 2. So it's going to look something like this. And yeah, I didn't think this one through, so it's okay. There we go. And
Withdrawing from method, sorry.
yeah, and so meh.
I'm withdrawing.
There we go. So it should look something like that. To be honest, the only level of detail I'd put is the fact that I've just listed that I've moved it up by 2. Now this one here, it says p brackets x plus 1. Put your hand if you can tell me what the transformation is. Mr. Schwab, what do you think? It's moved to the left one. So we're going to take our picture and we're going to try to move it to the left. Okay. So it's going to look something like that.
It's like a really long nose and a mouth and a chin.
Put your hands up if you can tell me for this next one down what's happened to it. Mr. Rosemeyer. It's moved to the right by 2. So for D, what's happened to this graph? What's the transformation for D? Mr. Schwab. It's reflected in which direction? Under. It's reflected in the x-axis. So whilst I'm doing these, or whilst you're catching up, I think I should also just mention this has been translated up by 2. This is translated left by 1. This has been translated right by 2. This has been reflected in the x-axis. And then, yes.
It's been dilated.
It's been dilated by what? Yeah, so this one will be dilated. Now, in order to demonstrate this is how I would go about doing it. So this is going to be stretched. It's going to be dilated by a factor of 3. Personally, I would draw a template of the original. So for instance, the original looks something like this. And then so for my actual graph, 3 times bigger means it's going to be looking like this. It's a lot narrower. There we go. So yeah, that way I know. So if I put that dashed line, I label that as p of x, and I label this one as 3p of x. That means that anyone who's looking at my graph knows that I'm being absolute. That is a dilation there. So it's just that I'm making myself very, very clear. So this is our dilation. By factor of 3 from the x-axis.
So you sort of have to guess in terms of dilation, you sort of like...
Yeah, because I gave you no numbers.
Yeah.
So basically that's why I suggest putting the little template so that I know that you mean that it's been stretched.
Yeah.
And the final one, put your hand up if you can tell me what F has done. Mr. Spaulding.
Is it being reflected
Yes, this is reflected in the y-axis. So in the y-axis, so that means where this graph was all positive, it's going to be all negative. It's going to be a mirror image. So it's going to look something like there we go. Consider the sketch of y equals p of x shown below. So again, they haven't given you an equation, but give a possible equation for each of the following in terms of p of x. This is a lot easier than it looks. You don't need to find all the x's and y's and things like that. It's just asking what are all the transformations. So if we look at this first one, put your hand up if you can tell me what you think has happened between this one and this one down here. It's been reflected. So this was reflected in which axis? X-axis. Perfect. So literally the equation just becomes, that's all you need to write. Just that it's put a minus sign in front. Okay. For part B, put your hand up if you can tell me what they think has happened to part B. Mr. Spalding.
It has been translated 3 places down.
And what made you say 3 places down?
Because it starts.
Because it's correct. I just want you to tell me why.
Because the middle, at the point of 0, it's 0
Yes, it is.
on
Okay.
the first graph.
Yep.
3 on the second.
Right. So just to explain, what Mr. Spalding was saying was that this graph translated through 3 units down. Because you see in the first graph, they said that's at 0 and the little turning point here is at -1. It said the turning point now is at -4. So it must have moved down 3 places. So it's gone down 3 places. So the new function would just be p of x, and then what would I put at the end? Minus 3. Okay.
That cute little excitement.
Now, we've got C. Put your hand up if you can tell me what's happened to C. It looks awfully close to the original, but a little bit different, Mr. Daniels.
It's been dilated by a factor of 2
It has been dilated by a factor of 2. What's made you say that?
because the turning point was at -1 and now it's at -2.
Exactly. So they're dilated by a factor of 2 from the x-axis. And the reason we found out is that the first turning point is at -1 here. And then the second turning, this one here is at -2. 1 times 2 is 2. So, and it looks like it's been stretched up. So this becomes, what would be the equation, Mr. Daniels, do you think?
Y equals 2p of x.
There it is. And that's the end of transformations.